In this video, what I want to do is take a look at the simplex method for solving standard maximization problems, but from a graphical perspective. So you've learned how to solve linear programming problems graphically, and now we're learning how to solve it using this more algebraic technique that uses some linear algebra called linear programming. And so I want to tie the two together so that you understand what is happening when you do the simplex method from a graphical perspective. So in this particular problem, I've already set everything up. We have our constraints up here. So we have three constraints. I notice that all the constraints are less than or equal to, which makes it a standard maximization problem. And I've created a table down here. And so this would be my objective function, p equals 5x plus 6y. And so in the table, I have identified the corner points of the feasible region. So this is the feasible region outlined by these four black points right here. And so we could tell just by looking at the table what the maximum value is, what the optimal value is. And so the optimal value is 19.69, and that occurs at the point 2.57, 1.14, which would be right here. And so if we click on these, we can see all of the four corner points of the feasible region. Well, that's the graphical method of solving this. From the simplex method point of view, when we create the initial table represents the feasible region at the point 0, 0. Okay, so the initial table is always the representation at 0, 0. In other words, the value of all of the active and inactive variables would be the value of those variables at the point 0, 0. And so we know by looking at this from a graphical perspective that that's not going to be the optimal solution. And so by looking at the initial table, we know it's not the optimal solution because we look at the bottom row and we have negative numbers. We have negative numbers in the bottom row. That's the simplex method way of saying, hey, this is not the optimal solution. So what we do is we create a new table. And we go through the process of identifying the pivot column, and then we identify the pivot within that column, and then we clear the pivot column. And by doing so, we've created a new table. I'll call it table number 2. Now, if you follow the procedures that I've outlined, what that will do is that's the simplex method way of saying, hey, let's go to the next closest point. So that would take you up to the point 0, 2. So in other words, table 2, using the simplex method, is going to represent the values of the active and inactive variables at the point 0, 2. Now, it could also take you over to the point 3, 0, depending on how you select your pivot. Sometimes you have a choice of two different ways of selecting your pivot. And so if you select a pivot one way, it may take you over to the point 3, 0. If you select the pivot another way, it might take you up to the point 0, 2. But regardless, table number 2 represents the next point in the feasible region. And so we take a look at the bottom row. And if the bottom row has any negative numbers in it, as it would at this point, then that's the simplex method way of saying, hey, this is not the optimal solution. Let's do it again. And so you would create table number 3. You would find the pivot column. You would find the pivot within that column using ratios. You would clear the column, and you create table number 3. And that would take you over to the next point. So it works its way around the feasible region, corner by corner, and that would get you over to this point. Now, we already know that this is our optimal solution. So what would table number 3 look like? The bottom row should be all positive numbers. And so that tells us, hey, the point 2.57, 1.14 is my optimal solution. So that's what the simplex method is doing. It works its way around, starting at the point 0, 0 to the next closest point, and then to the next closest point until you get to the optimal solution. So you can tell how many tables you're going to have to create just by looking at this graphically. So we have the initial table. This point would be table 2, and then this would be table 3. Now, if we have more than 2 variables, this particular linear programming problem only has an x and y. If you have more than 2 variables, if you have a z, then you're working in 3 dimensions and we can't graph it. If you have 4 variables or 5 variables, then you're working in a multi-dimensional object, but the idea is still the same. The simplex method would be working its way around all of these various points in this multi-dimensional object until it finally reaches the optimal solution. But by the time you get to a problem like that, you really need to know how to program this into a computer using a computer language. All right, so I hope this helps to understand a little bit better of what is actually going on when you're using the simplex method.